Welcome back. I'm talking to Andrew Johnson about the evolution of planet Earth and how it may have formed, and the work of Peter Woodhead, who has come up with quite an interesting theory which seems to tie everything together. Now just tell us about, is there any other research which suggests there might be, say, underground oceans or water under the ground?
Well, this is a key one, Richard, because we had one of those weird synchronicities in that I took quite a long time to go through this with Peter. He'd sent me a lot of the calculations, some of which he'd redone. You know, I knew that I needed to go through this carefully. We put these calculations together. I threw some of them out. I sort of adjusted some of them. I reformatted them. I didn't really change anything of the essence of what Peter had said, because I think he was right. But then we made a YouTube video. We posted this video. I posted this video. I think it was the 12th of June 2014 when I posted this video, and we talked about the origin of the oceans possibly being the result of this ice core originally. And then we found that there was an article published in New Scientist called, and the title of it was "Undersea Ocean Discovered." Yeah. And they put this depth of it, and Peter had calculated where he thought this boiling layer was, and I think the depth was around about 400 kilometres. And guess what? The New Scientist article said this undersea ocean was discovered at a depth of 400 kilometres.
Right.
And why they'd come out with this is they'd come out with this research because of a mineral called a rock called ringwoodite. And ringwoodite is like a type of rock that I think is about 1 or 2% water. It's actually got water in its structure.
Yes.
And if you calculate the thickness of this layer which they'd given, and then you calculate the total volume of that layer based on the current circumference of the Earth, and then you multiply that by 1.2%, the volume of water that you come out with is still greater than the volume of all the oceans currently on the Earth. So in other words, the volume of water that's still down there in this ringwoodite layer is greater than the current volume of all of the Earth's oceans, I think by about a factor of 5. And these are things that I think they calculated, and we'd done similar calculations too, just on, it's basically simple volume calculations, it's no more than that.
So you think that's acting as some sort of buffer?
Well, essentially what Peter had said when we originally did this idea that the Earth was a frozen core, and then outside of that you'd have this boiling layer. So outside of, and when that had all gone, you'd essentially have this layer of what we called slush. He called it slush because it wasn't water and it wasn't ice, it was something in between. So we didn't know what to call it, but this ringwoodite fits that description. It's not water, but it's not ice, and it's not, but in this case, it's not totally rock. It's got water in it, so it's a water-bearing rock, which obviously would be the perfect medium for where this water was actually was under the crust of the Earth. So in other words, the simple statement of that article was that there's a lot more water lower down underneath where all these volcanic layers are, where the hot lava comes out. There's actually water below that, and this was something which was never really discussed that much until quite recently.
So let's just consider what you're saying then and go down through the layers. Can we do that? We've got the Earth's crust. You don't refute that.
Correct.
And as you get further down, tell us what you...
well, obviously we can see from volcanic activity that we've got hot layers of molten rock, not too far below the surface, and you get what they call magma coming out of volcanic craters, which is maybe, I think, goes down to about 4 or 5 kilometres below the surface or something like that, but only in certain regions of the planet where you get this coming out. So we've clearly got hot material under the surface at certain points in the planet. But if you try and go below that, I think the deepest borehole that's ever been drilled anywhere, I think, is something like 7 kilometres deep. So they've only ever drilled down the 7 kilometres to actually sample rock and materials that are there, and it does get quite hot down there apparently. Right. But below that, what they're going on is seismic readings. So they fire these, they set off charges or whatever, they wait for earthquakes, and they make seismic readings, and these then allegedly are refracted through different layers of material, and the seismic readings end up being picked up at different stations. and it's a bit like an optical method where light is refracted through a lens and different types of medium.
Different types of wave will travel at different speeds
exactly.
through different mediums.
Through different mediums,
so they can try and guess what material it's made from.
Right, and the wave will get refracted, and it's the same. That's how they do seismic readings, and that's how they've allegedly deduced that there are different. There's a liquid layer lower down, and I think they say there's a liquid layer of iron at the centre because that absorbs some of the seismic signals.
So are you saying then that the water that's inside the planet, which may be high pressure steam now, can then bring about magma and volcanoes? Can steam get that hot?
Well, not exactly, because what we would argue is that the heating is going on higher up in the crust. In other words, as you go down through the layers, as you were sort of suggesting, initially it's hot, but then it'll start to get cooler. So when you get closer to the centre of the Earth, you've actually got a cooler layer, and the centre will be probably a relatively cool gas. Certainly not much. I don't know. It may be hotter than standard steam because we don't know how much pressure is there. But we're not dealing, as we would argue, with a high density, hot, high pressure, molten iron and all of that stuff. We don't think that's there. We think that the Earth's magnetic field, for example, is produced by another method.
Now, that brings us nicely onto other theories that I've read about, the hollow Earth. Because is that essentially what you're saying, or not?
Well, it's similar to that, and this is why I wasn't, when I initially came across this, I wasn't initially attracted to it, because I thought there's no way the centre of the Earth is hollow, because that just, the density measurements and so forth would not allow us to have that. But when I've looked at it more thoroughly with Peter's research, I do think, well, maybe yes, the Earth is hollow inside. But then you get into these other sort of areas of more contentious things, like the trip of Admiral Byrd. Did he go into the hollow Earth? And Olaf Janssen's story. And I covered all of that in another presentation, and we're not going to cover that here because, frankly, there isn't time. But my summary of that is I don't think that we've got this situation where people inhabit the inner Earth. There aren't these races there, I don't think. Certainly not at the depths of thousands of kilometres. There may be various cave systems which are a few kilometres down which have people living in them, for all I know. But this idea of having a whole race of extraterrestrials living inside of the Earth, and there's various passageways to that, I don't currently go with that idea.
Right. But let's just say then, let me just draw for this, because I can't get my head around the maths, because it's a calculus. So let's just say then you've got a sphere which is hollow, but it's got a certain thickness to it. Yeah, I've drawn my sphere there. Okay. Okay, we're on the surface there. Yeah. Mm-hmm. What would happen if you were inside there like that? Would there be gravity pulling you down there, would you say, or
what would happen,
or would you float towards the middle?
You would essentially float towards the middle, much as you see in that NASA video. Because
right, yeah. So we'll go back to the bubble.
Yeah.
So something which is quite massive or got heavier than water, say. Yeah. It's gonna. Well, no, you said if it would go to the edges, would go to the edge, and the
so in other words,
but the gas, the bubbles would go to the centre.
Yes.
So it would depend on your mass whether you would go towards the outer or the inner.
But it all gets very complicated because it's not something we can eat apart from the bubble experiment in the NASA space station. It's not something beyond that we can easily reproduce experimentally. This then gets us onto the whole idea of how gravity works. We make certain assumptions about gravity, but it is true. Whatever we said in this program, nobody quite understands, at least in the white world, what produces the force of gravity. And this has been one of the major sort of quests in physics, as to explain where it comes from. Yeah,
it's Newton's law of gravitation is an observation, not an explanation.
Yes, and it makes predictions about what will happen when you throw an object or you project it at a certain speed away from another body of a certain mass and all of that. And it does appear to sort of be fairly accurate for that. But what we then got onto, and this comes onto it very recently, that was a chap had contacted us about what's called the electric universe theory, and he was arguing that the force of gravity is a result well, this is what the electric universe theory says. This is Wallace Thornhill and David Talbot that have come up with most of this, mainly Wallace Thornhill actually. And he argues that the force of gravity is produced by dipoles, essentially in atoms. And if you look at a video he's done called Understanding, The Long Road to Understanding Gravity, which was only posted in the summer of 2015, he goes through this idea that the Earth's gravity is produced by dipoles in the Earth's the mass that's with just makes up the Earth, and he actually puts a picture up where he thinks that as you go towards the centre of the Earth, the force of gravity changes, and you will actually get a kind of a negative force of gravity as you go into the Earth and you're going towards the centre. So in other words, without he's not spoken to us about this, but he actually agrees with the proposal that the Earth wouldn't be a solid mass at the centre, that the gravity would work differently.
All right, Andrew. Well, mind-boggling stuff. And we're going to talk more about the impact of this theory on the universe and the wider solar system after the break.